Refraction, as we know from standard grade, is the changing of direction of light as it passes from one material into another. Changes direction, as you'll see later, because it changes in speed. So we did a simple experiment with a semicircular prism, put a light into that prism at a certain angle, and it will be refracted at a certain angle within it. So we noticed that for all the angles that we used, they were all bending towards the normal as they went into the material itself. So that just shows one of those possible angles. We repeated that for at 10-degree intervals and figured out a relationship between sine theta in the air and sine theta in a medium. Found that that was in direct proportion. So you got a best fitting straight line through the origin, which means direct proportion between sine theta in air and sine theta in medium, or sine theta in glass, as it was here. So we can say that those two are in direct proportion. So there must be some kind of constant there. So by simple rearrangement, we found that sine theta in air divided by sine theta in the medium is equal to some sort of constant k, and we established that that constant k was equal to n, which is the refractive index. Now the refractive index is just a number. It's a number that tells you how much light bends. So if something has a refractive index of 1.5, as the glass that we used did, then that means it bends light by a factor of 1.5. That's what it really means. So this is our equation here, sine theta in air over sine theta medium. So we'll look at a couple of different versions of that equation, including the one that you'll find in your data booklet. So if you've got a ray of light coming in air at a certain angle, when it goes into the medium, because it is more dense, it will slow down because there are more particles in the way, and that will cause it to change direction. It will bend down towards the normal. So you could project this light from this side and it would still follow the same path. So that path is reversible. It's just that the way that the light bends as it moves from one medium to another changes. You know, as it goes into a more dense medium, it will bend down towards the normal. As it goes into a less dense medium, it will bend upwards from the normal. So that's all to do with refractive index. Refractive index tells you how much that light will bend. So we applied that to one particular example, finding the refractive index for clear plastic from this diagram here. In the original question, we've got the angles in black, but those angles are not between the normal and the ray of light, as they should be. That's why the normal is there. We measure everything from the normal. So if you're using an angle in the refractive index equation, it must be between the ray of light and the normal. So sometimes they'll give you another angle, so it's just a case of taking that away from 90. So we can apply this equation that we just proved from experiment. Sine theta in the air divided by sine theta medium. So sine 60 divided by sine 36 will give us 1.47. But that's not the end of it, because that is the equation here that you'll have in your data booklet. It's sine theta 1 over sine theta 2. So you won't always necessarily be told which angle it is, you know, which medium that angle is in. So we always take sine theta 1 as being the less dense material, and sine theta 2 as being the more dense material. So medium 1 is normally air. 99% of the time it's going to be air, and medium 2 will be some sort of more dense material, whether that's glass or whether it's plastic or water even, you know, something like that, where light is going to travel less fast. Ray always bends towards the normal in a more dense material. Sometimes the formula is given as this, you know, where I is incidence, sine of the angle of incidence, and sine of the angle of refraction. N is always greater than 1. That's because the angle on the bottom here, sine theta 2, is always less than sine theta 1, because when it goes into the more dense material, i.e. the one that is represented by the bottom of this equation, then the angle will reduce. It will always reduce. It will always bend down towards the normal. So theta 2 is always less than theta 1, which is why we've always got to have that round the correct way. One more example in a minute. Applying it to emerging from a more dense material into a less dense material, so flipping it round the other way this time. We can still use the same equation, but we've just got to make sure that if we're always putting the less dense material, usually air, the angle that it is in air, on the top. So that's the one we're trying to figure out here, so you can just move things around to figure that out. The slightly difficult thing about this question was it was looking for the angle between the ray which is refracted and the surface of the glass. So we first calculate the angle between the normal and the ray, and then take that away from 90 to give us our final answer here.